Good morning. So, I wanted to take a minute here and follow up with the iron lab and make sure that everybody's feeling comfortable with the calculations. So I'm going to go through a sample calculation with some experimental data from one of my students' labs from a few years ago, and also to clarify significant digits for this lab. So if you look at the instructions for the lab, it says that we should dissolve 0.2810 grams of this iron compound. And in my experience, the lab managers, when they make the solutions, have been pretty good about using this exact mass. So we're going to go ahead and use that so that we can have 4 significant digits for our work. So in order to figure out how many milligrams of iron we have in our sample, we know that we're taking this mass and we are dissolving it in 1 liter of water, and it was a volumetric flask, so we've got plenty of significant digits there as well. Alright, so standard calculations here from Gen Chem. We are converting grams to moles, and then we're going to convert grams of this thing into grams of just iron. And that's why we have to go through moles here. So if you look at the molecular weight here and go through that calculation, the molecular weight for this entire compound I calculated to be 392.1294. I'm tired of writing that, so I'm just going to write iron X for 1 mole of iron X compound, and that does include the 6 waters, so if you're doing that calculation, make sure you do include those. And then, of course, 1 mole of this iron compound contains 1 mole of iron, and we can convert back to grams of iron by itself. So that's 55.845 grams per mole of iron. And so what I get when I do that calculation is 0.04002 grams. So that matches up pretty well with the 0.04. But of course it was in milligrams per milliliter, so let's look at that real quick too. So and this is 1 liter, because that's what we had right here. Alright, so the easy way to look at that is if we have 0.04002 grams of iron in 1 liter, and then we think about converting that into milliliters, because that was the unit that was listed on the container, then that's fine. But it was actually milligrams per milliliter, and so if we think about 1 gram, we've got 1,000, and our thousands are just going to cancel out, and so we just go straight from grams per liter to milligrams per milliliter of iron. Okay, so that should get us the rest of those significant digits there, so we actually can include a few. Alright, so the next thing to look at is, of course, just this quick reminder that when we dissolve the iron tablet in our 25 milliliters of hydrochloric acid, there was our tablet, and it was supposed to have 65 milligrams of iron in it. We took all of it and we put it in our first volumetric flask, so 65 milligrams is in here, and then we dissolved that to 100 milliliters, and then we took 5 milliliters of that sample and we diluted it up to 100 again. So now we have 1/20th of 65 milligrams in here of iron, and then we took 10 milliliters of that sample and dissolved it up to 100 milliliters again, and so now we have 1/20th times 1/10 of 65 milligrams in here, and that should be what our expected number of grams is, which is getting pretty small, but if you'll notice, in the lab I ask you to use micrograms, and so if we convert milligrams to micrograms, then we can take 65 divided by 10 divided by 20 times 1,000, and we're expecting 325 micrograms of iron in this sample. And that's total, that's not a per milliliter unit. So this is just how many total micrograms of iron we are putting in that flask, okay? And the reason I'm doing that is to be consistent with how I'm going to look at the rest of those calculations. And you can convert these, of course, into micrograms per milliliter if you want to, but I'm not going to right now. Okay, so now let's think about those standard solutions. So in the standard, we had one flask that contained 1 milliliter of the standard. We had one with 2 milliliters. We had one with 5 milliliters. And we had one with 10 milliliters. Okay, and in our sample over here, in each milliliter, we have 0.04 milligrams of iron. So that means that for this sample, we have 0.04002 milligrams of iron. And in this one, we've got twice that because we had 2 milliliters. And we had 5 times that over here, or 5 times this one, so that's 2.0. I think go like that, milligrams of iron, and then we have 4 milligrams of iron in this sample. And you can also convert these, of course, into micrograms, and so that becomes 40.02 micrograms, and this is total, not in a micrograms per milliliter, but just total. This becomes 80. And this is 200, and this is 400. So we can see as we are comparing that what we are expecting to have in our flask is about 325 micrograms of iron, and that is a little bit less than our 400 micrograms of iron that is in our largest data point on our graph, all right? So now we need to look at the absorbance. So I'm going to use the absorbance values that my student took a couple of years ago. So for her absorbance values, she got 0.138 for her 1 milliliter sample, 0.218, 0.448, and 0.832. And don't worry if yours are a little bit different than this because they tend to vary a bit. And then for her unknown, she got 0.517, okay? And so as expected, hers are in between, and actually her unknown was supposed to have 45 milligrams of iron per tablet, not 65 like yours, so you should expect that your unknown probably will have a higher absorbance than this. So just kind of keep that in mind. All right, so now doing this calculation, you used your experimental data to get a graph. So this student had a equation like this. And so just as a reminder, y is the absorbance and x is the concentration. And so you're going to use your absorbance for your unknown and plug it in for y, and then solve for your concentration of your unknown. And so using her data, if I plug that in, I get x equals 239 micrograms. So now, this isn't, of course, the total answer. This is the total number of micrograms in her diluted sample right here. And that's not micrograms per milliliter, that's just total 239 micrograms. So now we did 2 dilutions One was a 1/10 dilution, so we're going to need to multiply by 10 to deal with that, and one was a 1/20th dilution, so we need to multiply by 20. And if I do that for her numbers, she gets 48 milligrams. If I convert this also, I didn't put that in, but anyway. There you go. So we get 48 milligrams, which is a little bit higher than what her expected 45 milligrams was, but given probably a certain amount of uncertainty in our pipetting techniques, probably a reasonable one. So hopefully your data will work out similarly well. I know there were a couple of people who had unexpectedly dilute samples, so you should still use your actual absorbance. But what you can do is you can try using that actual absorbance and then getting your answer, and then you can guess that maybe I diluted this an extra time, and so try doing an extra times 10 and see how that goes. But anyway, you should just make sure that you explain it either way, because experimental data are what they are. And so, you know, if we had some difficulty with our lab technique, that sometimes happens in lab. So we just explain it, and then we try to make sure we don't do that next time. So hopefully this clarified any calculation issues that you might have been having, and that the rest of that lab write-up works out just fine. Let me know if you have any questions.